So, welcome to this particular module, and here we are looking at the oscillators. So, what are oscillators and how we can design those oscillators, right. So, if I clap my hand, you can feel the sound, right. Why this sound is there? Because I am pressing air between my hand, right. I am pressing air between my hand. So, if I clap it in particular fashion, my sound is different. That means there is oscillation that I can create by pumping something, is not it. Same way, what are the oscillators within your body? Do you have any oscillators within your body? Have you ever thought of that there are oscillators within your body? If you remember, we have talked this thing in your theory class, right, that our body also has a lot of oscillators or organs which work similar to an oscillator, right. So, in the electronic circuits, when we talk about electronic circuits, how the oscillators are designed and what kind of oscillators are available, and if I know a theory of an oscillator, can I design this oscillator in the experimental form and can I use it and see the output signal as an oscillation, right. Input would be noise, we have seen this, right. We have seen Barkhausen criteria, if you remember, right. The gain into beta, which is a feedback, so mode of A into beta should be equals to 1, and the phase shift should be equals to 360 degree or 0 degree. So, this theoretical knowledge we already have. Now, let us quickly once again see if you do not remember what are oscillators, and then we will move to the experiment part. Here in this particular module we will see several oscillators, and we will also see how to design a circuit in a multisim. So, we will see the oscillators designed in the multisim and see how the oscillations are formed. We will also design the oscillators using the breadboard and the equipment that we have and we love, and we will see what kind of oscillations we get at the output of an oscillator. So, when I talk about electronic oscillator, I had to again think about my operational amplifier, right. Operational amplifier is our theme, and we keep it at the central of this particular course, and then when we talk about operational amplifier, we also talk about some MOSFETs, we also talk about some integrated circuits, and we combine this thing to see their applications. That is what we are learning in this particular course, right. So, let us see how the oscillators are, or the theory of oscillator, and then we will see quick examples and we go to the experiment part. So, if you can see on the screen, oscillators, right, oscillators are used in many electrical and electronic circuits, correct. Oscillators are used in many electrical and electronic circuits. Okay. Next, it provides a basic block, basic clock signal that is used to control the sequential action of the entire system and synchronize its various stages. That means that oscillators provides the clock. That means if I want to give a clock to my electronic module, I can use oscillator, right, and the waveform generated at the output of the oscillator can be used as a clock signal to the further electronic module, right. That is what I am writing here, that is, it provides a basic clock signal that is used to control the sequential action of the entire system and synchronize its various stages. So, if you want to synchronize these various stages and use for the controlling the sequential action, then you can use the oscillator, alright. Oscillators basically converts the ADC input into an AC waveform, into an AC output. So, AC outputs are always with some frequency. DC has a frequency of 0 hertz. We all know DC has a frequency of 0 hertz, right. So, this output can have a wide range of shape and frequencies. That means you can design oscillators with various shapes and frequencies. You can have a square wave oscillator, you can have a sine wave oscillator, and then you will see what kind of shapes and frequencies we can generate using the oscillators. Oscillator is nothing but basically an amplifier with positive feedback or regenerative feedback in phase you see in phase. So, let us see what is in phase and what is out of phase, what is in phase and what is out of phase. You see, if I apply input signal, if I have the output signal, this is input, this is output, the phase of output is similar to input signal. But if I say that my output is like this, my output is out of phase, my output is out of phase. So, what is saying that an oscillator we can generate or we can design an oscillator by using an amplifier and a positive feedback, by using an amplifier and a positive feedback or regenerative feedback which is in phase, and one of the many problems in electronic circuit design is stopping amplifier from oscillating while trying to get the oscillators to oscillate. Alright. So, the point is that if you want to create amplification factor, then like we discussed in the theory class, we have to apply a negative feedback. If you want to create a oscillation or oscillatory action, then we have to give a positive feedback or regenerative feedback, and in case of positive feedback or regenerative feedback, the phase is in phase and it becomes an oscillator. Now, we will see that an oscillator is an amplifier. We can see that oscillator is an amplifier which uses positive feedback that generates an output frequency without the use of an input signal, right, that we have already seen in theory class, that the oscillator is a circuit which can generate the output, which can generate the oscillatory output without the use of input signal, without the use of an input signal. That means the oscillator is self sustaining, oscillator is self sustaining. Okay. Now, when we talk about oscillator, what it requires? An oscillator has a small feedback amplifier, small signal feedback amplifier with an open loop gain equal to or slightly greater than 1 for oscillation to start, but to continue the oscillations the average loop gain must return to unity, right. That means initially your gain can be greater than equal to 1 and it can be greater than 1, and then once you want to sustain the oscillation, it should be equals to 1. That is why when we write gain of an oscillator, its gain is equal to 1. But if you write the feedback formula, then we write A into beta should be equal to 1. We also write A because greater than equal to 1, but initially greater than equal to 1, later on it should be equal to 1. That is why we write both the symbol greater than equal to. Okay. So, this is about your oscillator, this is about your oscillator. So, in addition to reactive components are capacitor, inductor, right, reactive components. An amplifying device, what is the amplifying device? Our favorite device, op amp, right. In addition to capacitor, addition to inductor, that is our reactive devices, we also have an amplification device or amplifying device which is an op amp or a transistor, It can be BJT, it can be FET, it can be MOSFET, it can be BJT, it can be FET, it can be any transistor, right. Does not require to be only BJT, right, does not require to be only BJT. Now, we will see what are the kind of oscillators. Now we already know, right, this is kind of refresher that what we have done in theory, that we know about oscillator. We know that there is a self sustaining mechanism, we know it is a positive feedback, we know that you have initially A beta greater than 1 and then suddenly you make A beta equal to 1. So, that you have the oscillations sustaining oscillations. Then we have to see that we also know that it is nothing but you have the op amp into the configuration. Now, let us see oscillators with basic feedback circuit. So, amplifier feedback will be shown as shown in figure 8 or is shown in figure 8, and what we see here, there is a open loop amplifier. So, there is a no feedback, right, open loop amplifier, no feedback, and then there is a attenuator. The feedback is here in, I am talking about the amplification factor. Okay. So, now you see this particular schematic. What you see, that if I apply input voltage, I have this input that goes to the op amp, but there is a output voltage which comes and attenuates through beta. So, I have a output voltage beta into V out, right, which is minus here and this is plus here. That means V in is plus, minus I have beta into V out that goes to my amplifier, So, now gain without feedback, if I have a gain without feedback, you know gain without feedback is very easy to understand, V out by V in. Gain with feedback, we have seen inverting amplifier, we have seen non inverting amplifier, right. So, this is a gain without feedback because there is no feedback. So, we have gain equals to V out by V in, right. Here A is the open loop gain of voltage, gain with feedback. If I say with feedback, that means this feedback if I consider, if I just consider this one, it is without feedback. If I consider this one with beta, then I have A into V in minus beta V out, we have to consider this one, right. So, my gain would be A into V in minus beta V out, or if I have V out, where here beta is the feedback which is in fraction. Now, generally you will see, or we have already seen, that for different value of A, my beta is only 0.01 or maximum it was 0.1. When it was 0.1, my output was oscillating beyond my control, right. That means that what we have seen, that the beta value is only fraction, of fractions when you consider the feedback or attenuation. So, if I consider beta as very low, extremely low, then I have nothing but A into V in, or this will be V out. So, A into V in is V out into 1 plus A beta, or V out by V in is A by 1 plus A beta, where GV is nothing but your closed loop gain, because here we consider the feedback, this feedback by given by the feedback network beta. So, now once we know gain without feedback, we know gain with feedback, right. Then what is this? So, oscillators are circuits that generate a continuous voltage or output waveform at a required frequency, the values of inductors, capacitors, resistors, forming a frequency selective LC tank circuit and feedback network. What it says, that the oscillators are nothing but a circuit that can generate a constant or continuous output voltage, all right, in a particular oscillation, right, or required waveform or required frequency with the help of inductors, with the help of capacitors, with the help of resistors, which can form the frequency selective LC resonant circuit. It also uses the feedback network. This feedback network is nothing but an attenuation network which has a gain less than 1. We have seen that beta is always less than 1, and we will see. So, we have seen in theory classes, right, that when you talk about RC phase oscillator or we talk about Wien bridge oscillator, your gain, if your gain was 29, then your beta was 1 by 29, So, if 1 by 29 is way less than 1, beta is always a fraction of the output voltage. So, anyway, the feedback network is an attenuation network that we know with a gain of less than 1 and start oscillations when AB is greater than 1, which returns to unity when AB is equal to 1. So, that is why we write A beta greater than equal to 1, cool, alright. So, initially it is greater than 1, later on we make it equal to 1, so that our oscillations are sustained, right. So, that our oscillations are sustained. Now, let us see further about the oscillator, and further is we will see a phase shift oscillator. We have already seen in theory what is a phase shift oscillator, right. What we have seen, that if I use one RC network, right, this is RC, this is second RC, this is third RC, that means I have first, second, third, 3 RC network, 1, 2, 3, right. Just if I do not use op amp, I can have a phase shift of 180 degree. Why? Because one RC, generally one RNC gives us 90 degree phase shift. One RNC will give us 90 degree phase shift. That means 3 RNC should give us 270 degree phase shift, right. But when we talk about phase shift oscillator, we always say no, RC, 1 RC will give 60 and 3 RC will give 180 degree phase shift, right. So, we have seen in theory that this is true only because we tune the RNC in a way to get a phase shift of 60 degree, alright. We tune the value of RNC to get a phase shift of 60 degree, otherwise R1, R and 1C generally is we get a phase shift of 90 degree, that means 3 would give us 270. So, anyway, now we know that we can adjust the RNC to get the phase shift of 180 degree, okay. So, we have 180 degree phase shift. Why we need 180 degree phase shift? Because let us say this particular circuit, if you see figure number 9, this figure, what we see here is that the input is given to the non inverting terminal of an operational amplifier. This is a non inverting amplifier. So, my gain is what? My gain is minus RF by Rin, right. My gain is minus RF by Rin. That means, if I have a voltage of 1, right, and my RF is 1 kilo ohm, my Rin is 1 kilo ohm, then my output voltage would be minus 1, my output voltage would be minus 1. So, what is minus? Minus is my phase shift. This is 0 degree, here minus means I have 180 degree phase shift. At the output here I have 180 degree phase shift, but to sustain the oscillation, right, or to start the oscillation or to maintain the oscillation, we know, right, we have seen the Bar-Hussein criteria which says that the feedback voltage back to the signal, back to the input should also have phase shift of 0 or 360 degree. But if I directly apply 180 degree, right, without the feedback network, then that criteria would not satisfy, and that means that instead of 0 degree I will apply 180 degree at the input and the oscillations would not happen, So, to get the or to satisfy the Bar-Hussein criteria, we have to apply a phase shift of 180 degree, and this further phase shift of 180 degree will give us. So, 180 degree is phase shift given by RNC, 180 degree is already there. So, 180 plus 180 will be 360 degree phase shift or 0 degree phase shift. This 0 degree phase shift we are applying in the input of the inverting terminal. That means, now I have satisfied one criteria of Bar-Hussein, which is my phase shift is 0 degree or phase shift is 360 degree, right. So, now you can use the operation amplifier, you can design a RNC or a phase shift oscillator, right, or you can say RC oscillator, and see on the breadboard how it works. But before we move to the breadboard, let us understand what I said it is similar thing what I said, which is written here. The phase shift oscillator can be designed using an op amp as shown in figure 9 and figure 10, figure 10. So, let us see here, right, same thing. There are two different configurations for the oscillator. The output of the op amp is fed to 3 RC network to produce a total phase shift of 180 degree, which is here, right. As the feedback is connected to inverting input, the operation amplifier is therefore connected into its inverting amplifier configuration, which produces 180 degree. This is not 1800, this degree should be subscript superscript. Okay. So, 180 degree phase shift, while the RC network produces other 180 degree phase shift, and total is 180 plus 180. We have seen already in this one 180, we have here 180. So, 180 plus 180 is what we are feeding back to the input. For the oscillation to occur, the gain of the op amp must be greater than or equal to 29. This we have seen how this 29 number came in the theory class, right. So, the gain should be greater than equal to 29. So, now one criteria is satisfied of our RC phase shift oscillator is that the input by the input to the inverting terminal or input to the oscillator is 0 degree or 360 degree, even it goes through the feedback network. Second is that our gain should be greater than 29 initially, and then it should be equal to 29 to maintain the oscillation, alright. So, greater than 29, and then that can be adjusted by. So, how can we adjust this gain of 29? We can adjust this gain of 29, we can adjust this gain of 29 by having RF and R1 of 29 and 1, 29k 1k gain of 29, right, because it is the inverting terminal. So, inverting terminal is this is minus 29 gain. Why? Because RF, my gain is minus RF by R1, right. So, 29 by 1 equals to minus 29, right. So, but this minus 29, do not worry about this minus 29, gain cannot be minus. So, that is why I said it can be 29, and if the gain is 29, we can adjust it by using RF, we can use RF and R1 or Rin. Frequency of oscillator, we have seen how can we derive frequency. Frequency of oscillator is 1 by 2 pi RC under root of 6. Right, 1 by 2 pi RC under root of 6. So, this is about your phase shift oscillator, this is about your phase shift oscillator. So, what points we have to note when we talk about phase shift oscillator, alright. The point that we have to note is that although it is possible to cascade only 2 RC stages to provide the required 180 degree, not 1800, 180 degree. Okay. So, this is my mistake. This degree should be in superscript, right. This is not 900, if you closely see this is the symbol of degree, this should be superscript. So, 90 degree, this is 90 degree, alright. So, although it is possible to cascade together only 2 single pole RC stages to provide required 180 degree or phase shift of 90 plus 90, the stability of oscillator at low frequency is generally poor. So, when the frequency is low, you will see the stability is poor. One of the most important features, of an RC oscillator is its frequency stability, which is ability to provide a constant frequency sine wave output under varying load condition. So, this is very important that the frequency would be stable even you keep changing your load. Even if you keep changing your load, you will find that the frequency at the output of the RC phase shift oscillator remains constant, and that is extremely important, right. Now, if I cascade 3 or even more 4 stages together with 45 degree, right, 4 into 45 degree. So, this is 45 degree, the stability of oscillator can be greatly improved, right. This you have to remember. Next one is RC oscillators are stable, provide a well shaped sine wave output with the frequency being proportional to 1 by RC. Therefore, a wider range is possible when using a variable capacitor, right, because it is now just depending on R and C, and frequency is inversely proportional to RC, and that is why we can see that by just changing the value of R and value of C, in general, if just by changing the value of C If you have a variable capacitor, then you can use a wide range of frequency, However, RC oscillators are restricted to the frequency applications because of their bandwidth limitations. Okay, is limited to produce the desired phase shift at high frequency. At high frequency, we have to produce a desired phase shift in the RC phase oscillator, but it is difficult to do that, and that is why they are restricted to only frequency applications of because of their bandwidth limitation. So, frequency of the oscillation of the circuit is given by this particular formula when n is nothing but number of RC stages in the circuit. So, in this circuit what are how many stages we have used? We have used 3 stages. So, that is why we have under root of 2 into 3, which is under root of 6. That is why we say f equals to 1 upon 2 pi RC under root of 6. Alright. Hence, this formula comes into picture, which is 1 upon 2 pi RC under root of 6. Alright. These points we need to note, so that we understand that when we actually implement the circuit, what is the output that we are expecting, So, now let us see an example. Let us quickly see an example. It is very important to solve a few examples. So, we get the idea of the how the oscillations will work, how the oscillators can be designed. So, we say that here the problem is problem statement, you read a 3 stage RC phase oscillator is required to produce an oscillation frequency of 6.5 kilohertz, If 1 nanofarad capacitors are used, means C equals to 1 nanofarad. Calculate the value of the frequency determining resistors, we have to calculate the frequency, right. Frequency determining resistors, that is means frequency is already given 6.5 kilohertz. We have to determine resistors, resistor value, and the value of feedback resistor, that means we have to value R in and we have to value R F, we have to value R in or we have to value R and feedback resistors. So, R F and R, value of R F and R. Okay. So, in this particular case, how we will find the values, these values. So, for that we have a formula that was extremely easy, and that is the formula which is 1 upon 2 pi RC under root of 2 times n, and n is number of stages, right. Now, how many stage oscillator is there? 3 stage. That means, our formula will become f equals to 1 upon or 1 divided by 2 pi RC under root of 6, right. Now, we know f, we know C, we know 2 pi, we can get R, right. This is what we are getting, right. So, here your R would be 9995 ohms or 10 kilo ohms, right. And the operational gain, operation amplifier gain, why? Because it is a phase shift oscillator, your gain should be 29, right. I verify it clearly, gain should be 29. So, the gain must be equal to 29 in order to obtain a sustained oscillation. We have seen what is the damped oscillation, we have seen what is the over oscillations or unsustained oscillations, and we have seen the sustained oscillations, right. So, for we want always a sustained oscillation. So, have sustained oscillation in RC phase shift oscillator, we require 29 should be the gain, right, must be equal to 29. The resistive value of 3 oscillations resistors are 10 kilo ohm, that we already got 10 kilo ohm, right. Therefore, the value of op amp feedback resistor RF can be calculated by RF, right. So, what is AF? AF is nothing but RF by R. We know RF, we know AF, we know R, we know AF, then from that we can find RF equals to AF into R. What is AF? AF is what is again 29, AF is 29. So, we write RF equals to 29 into what is R? R is 10 kilo ohm, 10 kilo ohm. When you do this calculation, you will find 290 kilo ohm as the value of your RF. You get value of RF, you have value of R, you have value of C, you have frequency, your oscillator is ready, right. So, super easy example and super easy solution. So, it is impossible for you to make a mistake, impossible for you to make a mistake. So, do not make a mistake if such as easy questions are there, right. We generally make mistakes when the questions are easy and that is very amazing. Generally most of the complex questions we are able to answer, but when you ask very simple questions, it is very difficult for us to answer, right. So, and the beauty is always in simplicity. So, find the simple questions, first try to solve the simple questions, then move to complex questions. If your basics are strong, your basics are strong, your all the other things would strong, right, other things would be strong. We always know this, right. The foundation of the building, it takes the maximum time. If you see apartment construction, you will see the maximum time comes in the foundation of the building, and then whole big apartment comes very fast, this whole big structure comes very fast, but the foundation comes at a long time, because if the foundation is not strong, the whole apartment would collapse, down, right. That is why whenever we are getting education or we are learning any subject, we should try to make our foundation strong, that means our basics strong, right. Complex questions is easy to solve, but if you know the basics, then it will be very easy for you to understand complex electronics as well. Not only forget about just this subject, any subject that you are learning, first understand what are the basic concepts, alright. So, that is why even you guys sometime may have feel that this we have learned in theory. Why we are repeating here? The reason of repeating is that now you have a different example compared to theory, and you will immediately see how the experiments are done. So, it is fresh in your mind that what kind of oscillators we can design, and how it will behave. So, coming to the experiment part, what we will see today? We will see a RC phase shift oscillator or a phase shift oscillator using an operational amplifier, right, with some values, So, what are the values? Values are 100 kilo ohms, values are 100 ohms, and there is a R and C. You can see this is C is 100 nanofarad and R2 and R1 is 100 ohms, right. So, we have these values. Once we design this, then what kind of output we will obtain. So, we have to do, first thing is we have to connect the circuit as shown in figure 11. So, we will connect the circuit which is shown here. Observe the output signal at pin 6. So, where is pin 6? You see 2, 3, 6, 4, 7, right, pin 6 output here. So, observe the output at signal pin 6 using the oscilloscope, measure the frequency of oscillation and match with the theoretical value, okay. So, what is the formula for frequency here? F equals to 1 by 2 pi RC under root of 6. So, if I put this value, I will write down the calculated value of frequency, and then I will measure the value of frequency obtained from the oscilloscope, alright. So, right now by the time we call Anil to help us to design the circuit, what we can do? We can calculate the formula of frequency, that is theoretical value, and then we will see the measured value, alright. You can see very clearly, extremely clearly here, right, that we have 3 capacitors, we have 3 resistors, 3 capacitors, 3 resistors, right. We have a operational amplifier, we have a feedback resistor, right, and this is a inverting op amp, inverting amplifier. Inverting amplifier, that means that the output will be 180 degree phase shift compared to the input. So, when it is out of phase compared to input signal, with the help of RC we can bring it back to the in phase. So, we can have 180 degree plus 180 degree 360 degree coming back to here A, and then our A is calculated as 29. Then when we apply input, we have to just measure the output, we do not have to apply input, we are just measuring the output, and the we have to apply the bias value, Okay. So, if you go back, what will be the answer? This will be close to 64. If you come back to the screen, this will be 6497.47. 6497.47 is the calculated value. If you come back on the screen, you will see that value of frequency is nothing but calculated value, theoretical value is 6497.47 hertz, right, and we will see what is the measure value of frequency. Okay. So, now let us come back to the breadboard. Let us come back to the breadboard. So, we were looking at the RC phase shift oscillator, and now we have to measure the output in the oscilloscope. So, he has already connected the bias voltage, and now he is connecting the oscillator, the output of the oscillator to the oscilloscope, So, what we see? We see that at the output of the oscillator, the frequency is 3.981 kilohertz, which is half of our theoretical, or 3/4 of we can say theoretical value, and that is again because the theoretical value we have assumed that the resistors would be exactly 100 kilo ohm, the capacitors would be exactly 100 nanofarad, but in actual experiments the capacitors values would not be exactly the one that we have considered in the circuit, and that is why you can see the change. However, one thing that we can see clearly is the oscillation occurring. Now, this oscillation occurs, and you can see peak to peak voltage is 19.6 volts or around 19 volts, because we have applied the we have a gain which is very high, and that is why we have 19.2 volts at the output of the oscillator. Alright. So, this oscillation, one thing you should understand is we have not applied any input signal. Now, if I change the frequency, what will happen? Because you can change the frequency, or you can change the signal by changing the resistors, right, by changing the resistors or by changing the capacitors. You can see that in the slide we have shown that if you have a variable capacitor, then you can change the frequency of the RC phase shift oscillator, right. So, here we are able to see how the RC phase shift oscillator can be implemented using the operational amplifier. See, now he is showing that if you change the feedback, right, if you change the feedback, what is the change in the oscillation? You see, if now he is changing the feedback, that is feedback resistor, and thus if the feedback is changed, you will see the oscillations at the output. You see, it is not there, it is dying, it is dead, right. If you see the oscillator output in the oscilloscope, you can see that now you cannot see any oscillations, right, because the feedback resistor has been changed. Okay, if you again put it back, you can just you can just show the oscilloscope. Now, he is again replacing the feedback resistor with the original resistors, and you can immediately see that you have the oscillations, right. So, from here what we understand is that if we want to implement a RC phase shift oscillator using operation amplifier, then we can implement it very easily using a breadboard, using a oscilloscope and using DC power supply. We do not require any input signal as you see, right, because input DC it comes from the noise, and then we have here we can adjust the gain and we can adjust the feedback such that you can have a sustained oscillation. But if you change the feedback, you can also see that you will see the signal is the dying, right. So, we have seen that we can have oscillations, sustained oscillations by changing the R and C, or in particular the feedback of this particular oscillator, and we were able to see what is the change in the output signal. At the same time, what we also are able to see is that if I change the feedback, then immediately my signal in the oscilloscope comes to 0, alright. So, what I understand and what I feel is, now you are at least able to understand what are RC oscillators, what are RC phase shift oscillators, why RNC are used, how many number of RNC we used, 3 number, that means we are getting 180 degree, right. We are using inverting amplifier, but in case of there are certain oscillators where it does not require any feedback in feedback in the terms of RC feedback or any kind of feedback, because the output is in phase with the input, because the same output we can give it back, right. So, in some of the oscillators we will see that there is no feedbacks required, and in that kind of oscillators, what are those oscillators or how can we design this kind of oscillators, we will see in the next module. So, for this module you look at the video once again and understand quickly what are the RC phase shift oscillator, alright. Till then you take care, and I will see you in the next module. Bye.